your quiz covers 4.4, which is more examples in induction. The more examples in induction means that it can test to any type of induction. There's no matter. So your focus is not just on strong induction. Because 4.4 basically covers the whole chapter 4 before strong induction. And then 4.5, which is strong induction. And 5.1, which is injective, subjective, bijective. And 5.2, which is compositions. I can tell you they're not easy topics, especially injective, subjective, bijective, and compositions. Those are not easy topics. So that's the plan. So I don't just want to do strong induction just because of 4.4. It's possible you'll get a regular induction as well. So the materials I covered last week, variations of induction, you should review that as well. Okay, so last week's material plus this week's material, and possibly one material sometime this week or next week. So 2 to 3 tutorials of material will be on the next quiz. Yeah, that's all I want to talk about. I already put all the exercise questions and stuff on Discord. I want to talk about a little bit about the channel. So this channel will lead you to a different channel, which is called tutorial 8 and quiz 3, which has all the videos, exercises that I want you to have a look at. So it's right here. It has solutions as well. And then I also created some summaries for strong induction, injective, subjective, bijective proofs. So you should read all of those. This whole channel that I linked to, just give it a read. Okay, read the whole thing. I wrote a lot of things. Give it a read. That's the first channel. And then I also gave you another channel because surjectivity is basically image question, the second direction of image question. So all the image questions I gave to you from before, you can redo them because I can simply just change the question a little bit and make it a bijective function. I mean a bijectivity question. So all the questions you did from before, the partition product one, the absolute value one, square root one, all those, just make sure you go back and redo them. And I already told you how to change the question so that it looks like a bijective question. So give all of them a try as an extra practice because they're basically the same thing. So there is not much to give to you. Just redo all the ones you did from before, the image questions. And because she already told you, the bonus question is gonna be about definitions or propositions for those sections. So I already took a screenshot of all the ones that could possibly be on the quiz. So those screenshots, if you know all of them, you're guaranteed 1% basically. Okay, so this 1% is literally given to you. So you'll be tested on one of those. So make sure you know them by heart. So not just read them and say, oh, I know already. You need to actually, state them, write them down on paper, make sure you actually know them. Especially like if there are some keywords like, for example, using this as an example, the inverse of a function that assigns to every y, every is a keyword, you should know that. We'll definitely check that, right? So those words, just don't just like have a brief idea of what it is. You should know the precise definition. Okay, that's what I'm saying. All those I already put those in the channel, so you can even either you have a textbook or not, it's right here. Okay, all the definitions and propositions that could be on the quiz, I already left them here, so just make sure you know them. Okay, I'm not asking you to memorize them, like actually try to memorize them word by word. I'm not looking for word by word definitions. Just make sure you actually know what it is and you can use your own word to write it down. Unless you really cannot do that, then memorize it. I don't encourage memorization, but if you really cannot understand and write in your words, then go ahead and memorize it. Okay, because getting the 1% is important. Other than that, I'm just gonna start. Last week I already talked about the concept of strong induction, and which just briefly recall the several differences you might have. One is you might have multiple base cases, and some of them might not start with one. Maybe you have like one n equals to 1, n equals to 2, n equals to 3, or n equals to 10, n equals to 11, n equals to 12, something like that. Okay, that's one of the thing. The second thing is your inductive hypothesis is stronger because instead of suppose P of K is true, you are supposing everything before K plus 1. So start from P of 1 all the way to P of K, they are all true. So if you imagine the dominoes, you push all of them down instead of just one of them down. Okay? And I also said for such questions, as long as you have a recursive sequence, which we also talked about, a recursive sequence means that your sequence depends on the previous terms. If you have a recursive sequence, just keep in mind the recursive definition. For example, here, this is a definition. Keep in mind both your IH and your recursive definitions will be used in your proof. So if you get stuck, you cannot get to your IH, then probably you need to use a definition. And if you get stuck again, maybe you need to use it again. Okay, so just bear in mind that it's possible you need to use a definition multiple times, and it's possible you need to use your IH multiple times. So you just keep trying until you can get whatever you get. So that's all I want to say before we start the questions. There are two questions. I want you to have a look at both of them and try to figure out if you can determine what induction you need to use. They both have two terms given to you, the first two terms, but one of them only needs induction, not strong induction. You should try to figure out which one and why, and how many base cases you need and such things. Okay, so give them a try. And as I mentioned last week, the key here is when you do the inductive step, do you need more than just POK? I walked around and I saw some incorrect answer already. The incorrect part is your base case is wrong. Let me remind you, the base case, you should start with the smallest number that the statement is true. Okay, so this is a statement, what is the smallest number and that the statement is true. Okay, you're looking for this, not this. This is not what you're looking for. Okay. Similarly here, although it says n greater than or equal to 2, but that's not what you need to prove. This is what you need to prove, right? So you need to think, what is the smallest number n that this is true, not the recursive definition. Okay, so if your base case start with 2, that's wrong for both questions. And if you don't know what is the smallest number, you can just read the question because they ask you to prove this for all non-negative integer n. So it means that it works for all non-negative integer n. And what is the smallest non-negative integer n? Right, so that's gonna be your first base case. If you need 101, then you should figure that one out, and so on. So don't make sure your base case is at least correct. Will I be getting meter back? I have no idea. You can keep asking me, and I will just keep telling you I have no idea because the TAs are not downgrading. I've sent them at least 3 emails to remind them. They're not marking, and I cannot force them. You know, it's not like I can knock on the door, put a gun on their head, and say mark. That's not how it works. Okay, so it's whenever they finish marking. I'm gonna take the first one up because I saw a lot of you finished it already, and we really have a lot of things to cover. So I'm gonna take it up, and maybe I'll give you slightly more time for example 2. We'll see. Yeah. So what do you guys think? Do we need regular induction or strong induction for this question? What do you think? Yes, this question we have to use strong induction. Okay. Some of you think it's because we have a recursive sequence which needs previous two terms. Some of you think that's why we need strong induction. That's not the reason. Okay. Why? Last week I already gave you a recursive sequence requires previous two terms, and it's a regular induction question, right? So it's not about being recursive. Okay, you can have recursive and you only need a regular induction. So what exactly changed? What exactly required me to use induction? Yes.
Again, being between 0 and 1, because we have to show that it's between two numbers. We never did that in regular induction.
Not really. I can give you a regular induction that has this. It's not about that either. Okay, so I can tell you just from reading the question, it's not possible to determine it. Okay, the real thing that happens in inductive step, it's when you actually try to prove it, you'll see that you need more than just POK. Because of that, I'm gonna start with inductive step instead of base case and IH. Because right now, I don't know which one I need to use. I don't even know how many base cases I need. I don't even know which inductive hypothesis I need to write because I don't know if it's strong or regular. So I'm gonna start with inductive step. Yes. It's recorded. I suppose it is. Yeah, it's being recorded. Okay. So yes.
When you have a(-1 and a(-2), can you assume it's strong induction?
No, just like here, I can change this to Fn equals to Fn-1 plus Fn-2. But this question is not a strong induction question. We did it last week, remember? I only assume for some k instead of all of the ones before. So that's not how we determine if it's induction or strong induction. Okay? The real thing happens in inductive step, and which we'll start with this. Okay, I'm gonna go there, check how many base cases I need, is it strong or irregular, then I'll go back and write the rest. So to prove this, let's figure out what do I need to show. So I need to prove this. So I need to prove 0 is less or equal to AK plus 1, which is less or equal to 1. This is what I need to prove. Okay, and AK plus 1, what does this equal to? AK plus 1 by the recursive sequence, the recursive definition, I know that this equals to 1 over 4 AK squared plus AK minus 1 plus 2. This is by recursive sequence, or recursive definition. Okay, so now, if we look at this, I know that, in fact, I need to show this expression is in between 0 and 1, agree? Because this is equal to this. I know this is what I need to prove. Okay? But to prove it, there is no information I can get from recursive definition anymore. Because recursive definition does not give me any inequality. I'm hoping to get an inequality. This is not going to give me any equality. The inequality I can get is, in fact, from IH, right? From IH. So you know that from IH, I can have information about, for example, AK. I know it's in between 0 and 1, right? So let's say that's something I need to assume. So from IH, although I haven't assumed it, but I can add it later, I know that AK is in between 0 and 1. Okay, so observe this. With this, I know that maybe I can square it, right? I can square all three sides. Because they're positive, I can square all three sides and get the same thing. So square them, I'll get this. I'll go 0 is less or equal to AK squared, which is less or equal to 1. But is this enough? Do you think this is enough for me to get this whole expression is in between 0 and 1? Not really, right? So what else do I need? Exactly. I also need to know about this, right? And what do I know about this? I need to know information about this from IH, not recursive definition. Does that make sense? It's about this term, and it has to be from IH. Because recursive definition is not going to give me anything. So I also need to know from IH, AK minus 1 is also in between 0 and 1. This is why I need strong induction. Does that make sense? Because here, as we said, we need this. And where do I get this? I need to get it from my IH. But this is not P of K. This is P of K minus 1. So I need more than just the domino in front of me. I need both of the two dominoes in front of me. That's telling me I need strong induction. Does that make sense? Yeah. So this is why we need strong induction, because I don't need it. Now compare to the question from before. Okay, so compare from before, you'll see that I also used something like of k blah 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 blah. But the key here is before I use multiple times, but they're all just recursive definition. Recursive definition is given to me. I don't need to assume it. I can use it for any k minus 1, k minus 2, k minus 3. Those doesn't require IH. I use recursive definition, I can use it for anything. Don't need to assume anything. The only time I use IH is here. This is the only time I used IH, and this IH is P of k. Okay, I don't need P of k minus 1. Does that make sense to you? So even though I have recursive sequence here and I use them multiple times, but that doesn't affect me because those are definitions. Okay, I don't need to assume anything when I use them. This is the only definition, the only assumption I used, and it doesn't require more than that. That's why this one is a regular induction. So now I'll go back to this question. I can finish the inductive step first, and then I can go back to write my inductive step. So now, thus, I can observe that there is nothing I need to do. I can just add those two terms together. So let's add them together. Let's call this 1, let's call this 2, add 1 and 2. I have 0 is less or equal to ak squared plus ak minus 1, which is less or equal to 2. And it's getting closer. I can add 2, on both sides of the equation. Is equal to 4, and almost there because I can just need to multiply that one with 4, and that's what I need. Okay, so the rest you can do it yourself. Actually, already because I'm worried you don't know how to do it yourself. Because this side you have 1 over 2, but we need 0. Here we need 0 on this side, but 1 over 2 is good enough to 0. So we're done. Okay. So this tells you ak plus 1 is in between 1 and 0. This is an inductive step. Okay, and from this inductive step, I see that I need strong induction. So let's do the hypothesis. So I'm gonna remove this part. Okay. Now assume there are several ways to do that. So I usually write like this. I copy the original thing down. For n equals to start with the smallest one, which is 0, 1, and all the way to k. For some k in natural. Okay, so now the key point here, we're down here because I still need to figure out base cases. And this k, does this k have any restrictions? What do you guys think? Do I need to write something like k greater than or equal to 2 here? Does k have to be greater than or equal to 2? Yeah, no, yeah, no.
No.
Why not?
This for all.
Not really. Okay, no, yes.
Would it have to be k is greater than or equal to 1?
That is correct. Okay, that is correct. The reason is, does k, what is this k gonna affect? It's gonna affect my inductive step. So how do you determine the restriction of your k? You check your inductive step. You check here. Okay, you check when you use your recursive definition. This is when I use it. I used it here. Okay, the restriction is on this. So you should think, well, can my k be 1 here? If my k is 1, I have a2 equals to 1 over 4, a1 squared plus a0 minus, a0 plus 2. a1 is defined, a0 is also defined, so k equals to 1 is okay here. Okay, why here is plus greater than or equal to 2, but here greater than or equal to 1 is okay? Because, well, when we use it here, your n is k plus 1. Okay, it's 1 n equals to k plus 1. So n has to be greater than or equal to 2 means that k plus 1 has to be greater than or equal to 2. So k has to be greater than or equal to 1. Does that make sense? Okay, it's because when you use it, it's for n equals to k plus 1. So the restriction is here. So I don't need to add anything here because natural numbers are already greater than or equal to 1. Okay, but for a long time, you need to add a restriction here. And now my final question is, how many base cases do we need and why? We know that the first one is definitely 0 because that's the smallest non-negative integer, right? So the first one, 0, which we all agree it's 0. I need to check. This one definitely needs to be there. A0 is 0, and we know that 0 is definitely between 0 and 1. So this is okay, but do I need the second one? That's the question. Do I need the second one? What do you think? So let me rephrase it, okay? Because you guys are CS students and you know recursion. Can I call the function itself and get this conclusion? Let's say you define the function in Python, and this function is going to tell you if this recursive sequence is going to be between 0 and 1. Okay? Which this one should be quite simple to define. I hope it's simple for you. Okay. Can you call this function? You call this function? Do you think once you call it, do you think it can tell you A1 is in between 0 and 1? Why not? Yes. Because then it's greater than equal to 2. That's correct. Okay. Because you can call it, yes, but that's the thing. If you call it, because your recursive definition is here, right? So if you call it, it's gonna use this recursive definition. So it's gonna use A1 equals to 1 over 4, A0 squared plus A minus 1 plus 2. But what is a negative 1, sorry? What a negative 1? It's not given to you. So even if you call the function itself, there's nothing. Okay, so when you define, you need to say for n's less than 2, right? And you define them properly. And you need to give them the initial condition, which are those two. Yes.
Why do we need to have that?
Why do we need to what? Sorry.
Why do we need to have n equals 0 to prove negative integers?
Because 0 is a non-negative integer. Right? It's not negative. Okay, so you also need the second one. Because inductive step cannot prove the second one. You need both, you check them and use them to prove the next one. Okay? So A1 is 1, which is also in between 0 and 1. Okay, so the key here is we use those two base cases to prove A2. Okay, and then you use A1 and A2, you prove A3, and so on. Okay, so A0 and A1, you cannot prove them using inductive step. Yes. No, because that one you can use the inductive step to get it already. Okay, so everything that you can get using the inductive step, you don't need to show them anymore. But if you cannot get, then you have to show them. Does that make sense? Okay, cool. Make sense? Oh my god, it's impossible for me to reach the next part. Okay, so we'll do example 2, and we'll do another tutorial on inductive surjective. Injective surjective algebra, because I don't want to rush through everything, because if I rush, you are not gonna get everything. It's more important to understand everything than rush through everything. So, example 2, after I talked about those, I want you to redo this question, or if you're only trying to solve it, try again, okay? And a few questions I want you to answer. One is, how many base cases do we need here? 2 is, do we need strong induction here? Okay, so those 2 questions I want you to answer me later. So I'll give you some time to work on them, and you can give it a try. All right, so I'm gonna take it up. So let's do a vote. Let's do a vote. Raise your hand if you think we need 1 base case only. Don't be scared. Maybe you're the only one who got it right. Okay. Right now, raise your hand if you think we need 2 base cases. Okay. Raise your hand if you think we need 3 base cases. So what about the rest of you? Not everyone voted. Let's do it again. Raise your hand if you think we need 1 base case. Okay. 2 base cases? 3 or more? Okay, 1 is correct. 1 is correct. Now, raise your hand if you think we need regular induction. Raise your hand if you think we need strong induction. Oh, that's great. That's correct. This is a regular induction question. Okay, it just looks kind of scary. It looks like it's a strong induction, but it's actually a regular induction, just like last week. Oh, actually, by the way, I don't want to give you the feeling that all Fibonacci numbers are regular induction. In fact, most of them are strong induction questions. Okay, it's just I purposely picked recursive definition questions that's only regular induction, just to show you that's not how we determine if it's regular or strong. But that doesn't mean every single of those are just regular induction. So don't make the conclusion like that. Okay. Anyway, again, since it's a recursive sequence, as we said before, it's possible that it's a strong induction question. So I don't know yet. Let's pretend I don't know yet. Obviously, I know right now, but pretend I don't know yet. So I'm gonna start with the inductive step and see if I actually need more than just one IH, and more than just P of K. So now I need to show P of F1 squared plus F2 squared all the way to Fk squared and then plus Fk plus 1 squared. This is what I have, and I need to show that this equals to Fk plus 1 times Fk plus 2. That's the P, that's what I need to do. But now, I notice that this part, it's basically my IH, right? This first part is basically my IH, so I can let it be Fk times Fk plus 1. That's the first part, and plus Fk plus 1 squared. This is by IH. And this IH is P of K. Okay? So now, am I stuck? What do you think? What can I do here? Well, this is not quite what I need, but that's okay. Why? Because I can factor out Fk plus 1. Why did it factor it out? Now what do I do? Yes. What does that tell me? What is this equal to?
Fk plus 2.
That's correct. Okay, so this part is Fk plus 2. This is by the definition. And we're done. That's all I need to do for induction. So now, if you look at this, you can see that during this part, when I use IH, I've only used POK. I did not use anything else. So I don't need a strong induction here. Does that make sense to you? You see that here? This part is only POK. So I can write my IH now. So assume F1 squared plus F2 squared plus Fk squared equals to Fk times Fk plus 1 for some K in natural. Do I need the restriction for K? Why not? Yes.
Because it works for all natural numbers. For example, Fk F1 is defined as 1 for all natural numbers.
Yeah, and basically also because the only place you use the recursive definition is right here. So this K, as long as it's greater than 1, greater than or equal to 1, we're good, right? So you're checking where you use the recursive definition, because that's where the restriction is. So this, as long as K is greater than or equal to 1, it's okay, where K is already greater than or equal to 1, so we don't need to add a restriction. What about base case? Why do I only need the first base case? One base case. So base case clearly is when n equals to 1, so let's write it down. When n equals to 1, I need to show F1 squared. F1 squared is 1 squared, which is 1. That's the left-hand side. So let me rewrite it as left-hand side. Left-hand side is this. And right-hand side is F1 times F2, which is 1 times 1, is also 1. So we can clearly see that they're equal to each other. So this is good. So the key here is, well, can I use the first one to prove the second one? Yes, right? Yes. Because why? Because, well, even if I cross all of those out, then if I know the first one equals, just add the next one, it works exactly like this. Okay, so the second one can be proved using the first one. We don't need to assume the second one. Does that make sense? Yes? No? I have 2 minutes. I'm not going to do injective, surjective, bijective. Actually, let me check if they have any question. So how do we know? As I said, depends on you know if P of 2 can be reached by P of 1. Does P of 1 implies P of 2? If not, you need P of 2. Anyway, before you go, there is example 3. This is the one that will help with a coding question I put on Discord. I don't have time to go over it, so I will send the video of me doing it on Discord. Hopefully, after watching that, you can figure out how to write the code. But that's it. If you haven't DM me, please do so, and I'll see you guys next week.
Yeah.